So my name is Brett Herrick, and I will be doing a presentation on solar energy for our Chem 112 class. So what is solar power? Solar power essentially generates electricity from sunlight, with the sunlight being in the form of photons. You can see here on the right there are photovoltaic panels, and on the left there is a concentrating solar power plant. So photovoltaic panels will, in essence, just convert sunlight directly into electricity through the use of solid-state semiconductors. They are up to 30% efficient, meaning that they will convert up to 30% of the sunlight absorbed into electricity. They are extremely adaptable, meaning that they can be put in a lot of different places. They can be put out in fields like you can see on this picture here, but they can also be put on top of buildings or parking structures. They can be put in small electronics like watches or calculators or phone chargers. I mean, they're really versatile. Concentrating solar power plants, on the other hand, are a little bit more roundabout in how they convert solar power into electricity. They convert sunlight into heat, heat into steam. Steam turns a turbine, and then it converts electricity. They can be up to 35% more efficient, which is a boon, but they're also a little less adaptable, and they need like a large space to put the thing in. They're best used in areas with high solar irradiance, and they also have thermal storage to help when there's no solar power at night. So how do photovoltaic cells work? So they utilize a effect known as the photovoltaic effect. Essentially, it's when photons from light excite an atom, and it can produce electricity through that. These are usually made from silicon, and about 95% of the photovoltaic cells that are used are silicon-based. Silicon, of course, is a group 4 atom, or group 4 element, meaning that it has 4 valence electrons, and these in the cells, the layers are crystal lattice works. So there are a couple of components that you need to know about. There's obviously the glass component, which has an anti-reflective chemical to help absorb more and reflect less. There is the negative terminal, which will serve as a channel for electrons when I talk about that here in a moment. And then there's the N-type layer. So this is particularly important in that it is doped or injected with a group 5 element, most commonly phosphorus. And this is important because group 5 elements have 5 valence electrons, so they are able to bind to 4 silicon atoms, they are able to bond to 4 silicon atoms, and then they will have 1 free electron that is able to just kind of float out there. Then there is the p-n junction, which is where the n and the p layers meet. And then there's the p-type layer, and this is kind of conversely to the n-type layer. It is doped with a group 3 element, most commonly boron, and because group 3 elements have only 3 valence electrons, it can bind to 3 silicon atoms in the lattice work, but then there will be 1 spot that is free. Then there is the positive terminal, and that is where the free electrons will come back through. So how does this entire thing work? So photons are going to come in, and they are either going to be reflected, absorbed, or they're going to pass through the cell. What we're interested in, obviously, is the photon that is absorbed, and those are going to go in to the p-n junction, and they will excite the atoms there. This will produce 2 things. It'll produce a free electron and then a hole where that free electron was. So the free electrons are going to go up towards the negative end, and because there are no spaces for them, they are going to keep traveling up and up until they hit the negative terminal, and then they are going to go out into the external circuit and power whatever it is that needs to be powered. The hole that is produced, on the other hand, is going to be filled by an electron below it. And then that electron is going to generate a hole, and it's going to be filled by the electron below it. And it's going to keep going and going until it has a hole down at the bottom by the positive terminal. The free electron that went and powered something is now going to come back in, and it's going to fill that hole, and the entire process is going to happen over and over again as more and more photons hit the photovoltaic cell. So there are a couple types of concentrating solar power plants. There are solar power towers and linear concentrating systems. You can see down at the bottom here, this is a solar power tower, and these are the linear concentrating systems. So solar power towers, other than being fun to say, are fields of mirrors that reflect to a central tower, and there is usually a receiver on this tower that is going to take all of the solar energy in, and it's going to heat up that receiver, and then that heat is going to be transferred to a liquid medium. Usually it's water. However, more advanced designs are increasingly using molten nitrate salt, and that's because it's a little bit more efficient. The linear concentrating systems, on the other hand, are U-shaped mirrors, and they don't reflect to a central tower. There's actually a receiver that goes all along the length of all of these, and you can see it here. It's kind of bright and hard to see, but you can see the receiver here, and it's going to be filled with a fluid which transfers heat to a heat exchanger, and in both cases, this heat will create steam in a boiler which powers a turbine, and I will talk about that just in a second. So it utilizes something called the Rankine cycle. Essentially, heat is going to come in, and it's going to heat up saturated liquid water, which is in this boiler here. That liquid water is going to get turned into high energy, high pressure steam, which gets pumped into this turbine here. And it's going to turn this turbine and create mechanical energy, and the work is going to go out in the form of electricity. As that steam loses energy and has less pressure, it's going to get pushed down through this pipe and into a condenser where it's going to be cooled. The heat is going to go out, and it's going to get turned back into liquid water and get pumped up through here, through the pump, and then directly back into the boiler, so the cycle continues over and over and over and over again. And that is how concentrating solar power systems generate their electricity, which is obviously a little bit contrasted to how photovoltaic cells work. So what are some of the advantages and disadvantages? I think that the largest advantage for solar power is the fact that it's just a huge source of clean power. In fact, it's estimated that about 50,000 exajoules of solar power is actually harvestable. There is way more that hits the Earth. I believe it's about 4 million exajoules. So only about 50,000 is harvestable, but to put that into context, in 2025, the entire world consumed about 460 exajoules. So we can harvest about 100 times more than we actually consume. We just have to build the infrastructure and more solar power cells to do so. It has a small carbon footprint. It doesn't generate, carbon dioxide in the same way that fossil fuels do. And it kind of beats out some of the other sources in this way. Geothermal and hydro are both limited by geography. Geothermal can only be used in certain geothermal reservoirs, and hydroelectric power is obviously confined to places where water is flowing. And it is a little bit better than hydrogen in that hydrogen requires fossil fuels to extract hydrogen from water, because it has to pass an electrical current through the water to actually get the hydrogen out. And it's adaptable as far as photovoltaic cells go. Like I said before, they can be put just about anywhere. I believe it's estimated that about 24,000 square miles of parking structures are in the US, and we could just cover those with photovoltaic cells and generate a ton of power, and we wouldn't have to use a ton of land. There are obviously some disadvantages to solar power. I mean, there's no perfect energy source. Hazardous chemical use. We need to use hazardous chemicals to create the photovoltaic cells, to create the mirrors, and we need to use a lot of metals and glass to actually make those things, and we have to be very careful about how we not only handle it, but how we dispose of things that we don't need. Otherwise, we could have an ecological catastrophe. Land use is specific to concentrating solar power. I mean, it happens with photovoltaic, but concentrating solar power is more egregious with the amount of land that it needs to use. It has to be in high solar radiance areas, and it can't just be put on top of a building like photovoltaic can. It has to be out in a field and have a large structure to actually work. It's also expensive. Photovoltaic cells for the average home cost at minimum $30,000 to install. And while there are some tax credits, that's obviously a pretty big disadvantage for the average consumer. You do get a return on investment. It's estimated that over 25 years, you'll save a minimum of $30,000, but obviously that's savings over a long time versus a high initial cost that you have to front to install them. And finally, probably the most obvious one is that it's intermittent. We don't have daytime 100% of the time, and obviously, the sun is going to be at different stages, and it's not going to be the same intensity all the time. There's seasons, so days get shorter, nights get longer. Cloud cover can affect things. And while there are things that try to help with this, like batteries to contain the solar power that they get during the day, or in concentrating solar power plants, there's thermal reservoirs that kind of hold the heat that they get from the day. It's not going to be continuous, and it's the same way with wind power, really. So I hope that you all learned something about solar power and that you are a little more informed about the advantages and disadvantages. And that's going to be it for my presentation. Thank you so much.